So we were working on this problem 21 last time, and I thought it might be instructive to try to rewrite this in terms of the other directions, if that's possible. And I was just looking at it, and I was thinking, oh yeah, it's if you look at it from the ZY plane perspective, you have this square surface, and so you could think about the integral being from 0 to 4 here and 0 to 4 there. The issue is that you're going to have two integrals, because this curve, this parabolic cylinder shape, is going to be the top of the volume for part of the domain, and this side part here is going to be different. So I'm going to give it a try. I think what we have to do is we have to find out what the intersection of these two curves is projected onto the ZY plane. So how the heck we do that? Well, I think what we do is we, at this point where they meet, the Z value is the same. So if we take them and we would say, actually it's simpler than I thought it was. So you get 4 minus, Z is equal to 4 minus x squared here, and this is that true? What value here is the same? It's actually the x values are the same, so that's not true. So what I'm looking for is, if I take this curve of intersection and I project it down onto this plane, so I can define my two regions. So they're going to have the same x value. So what you would do, I think, is you would take z equals 4 minus x squared, solve for x squared, so x squared is equal to 4 minus z, and x squared, you can do the same thing here, y is equal to 4 minus x squared, or x squared is equal to 4 minus y. So you set these equal to each other, and you get 4 minus z equals 4 minus y, and so what you find out is y equals z. Okay, so this curve, which is this point of intersection, which when projected down onto this plane here, is actually a straight line. Okay, so let's get a piece of graph paper, and we might be able to prove that they actually are the same. We could do both integrals. So what I'm doing here is I'm going to draw a line, which is z equals y or y equals z, and you can see we come out to 4 here and 4 there, so the actual region that we're talking about, there's two regions. There's one here, 1, 2, 3, 4, like that, and there's the second region like that. And so if we drew these rectangles to help us figure out what the limits were. So for this region it's going to look like that, and for this region it's going to look like that. So I think, and the other thing is we have to write these as x is a function of z instead of z as a function of x. So if we solve this equation, which we've already sort of done up here, so you get x equals plus or minus the square root of 4 minus z, and here we'd get x equals plus or minus the square root of 4 minus y. And so this part right there. So let's call this Z. Here's Z, and here's Y. So the function that applies to this region would be this curve. So that would be x equals 4 minus y. And for that region, you go from y equals 0 to 4, and then up here, that would be this one, which is y equals 4 minus x squared, or x equals, and these are, I forgot the square root part. I think they're both the positive the square root, because this one is in the positive z direction, or positive x direction. This thing loops around kind of like that to go, and then this one would loop around kind of like that. So they're both in the first quadrant, so I think that they're plus the square root of 4 minus z would be that one. So I think you're going to have two volumes, and the first volume is associated with, let's do this one first, this lower triangle. So we're going to integrate from y equals 0 to y equals 4, and the second limits are going to be the boundaries of this rectangle, which is going to be go from z equals 0 to z equals y. And then we have the third integral, which is from x equals 0 to x equals, and it's this one, so it's going to be the square root of 4 minus z, and we're going to have dx dy, or dx dz dy, dx dz dy, because we got x, z, and y. And then you've got the second area, which is this upper triangle. It still goes from y equals 0 to 4, because we go from here to here. Now, the second integral goes from z equals y, so that's the diagonal one, up to z equals 4. And then we have the integral, and the function that applies to that region is going to be, you go from x equals 0 to x equals the square root of 4 minus y, and it's going to be still going to be dx dz dy. And you add those two together, and it should end up being the same integral that we got here. In this case, because of the way these cylinders are oriented, the cylindrical parabolas, or whatever you want to call them, we only had to have one integral. And so in the xy plane we went from x equals 0 to x equals 2, and then in the y direction we went from y equals 0 to y equals 4 minus x squared, and then up in the z direction we went from 0 to 4 minus x squared. And I think if we do all of those, if we did those integrals, we'd end up with the same value. Just thinking how hard the problem is. Yeah, this one's going to be a heck of a lot easier. The problem you're going to have here is that when you integrate with respect to x, you're going to have the square root of 4 minus z. Then you're going to integrate with respect to z, so you'll get z times the square root of 4 minus z. Then you'd have to use a second kind of u substitution to solve for that, for the next integral. And I mean, not that it's not doable, it's just more difficult. So let me know on Tuesday if you understood what I did there. You know, if I wanted to, is there another direction where it might? Yeah, I think it would just be just as easy if I did the XZ plane, and then I integrate it. So I'd do dx, dz, dy, I think would be the same level of difficulty. So let's do that one. It's just because of the alignment of these. This parabola is, well, this one's parallel to the z-axis. Anyway, let me write it out and see if you agree with me or not. So what we do is we integrate, this part here is going to be the top surface now. So what I have is this in the xz plane, and if I draw a rectangle this way, I'm going to integrate from x equals 0 to x equals 2. And then in the z direction, I'm going to go from z equals 0 to z equals 4 minus x squared. And then I'm going to integrate with respect to y. So I'll integrate from y equals 0 to y equals 4 minus x squared. And then I have dy, dz, dx. So all we've done really is just switch these two and switch these two. So those two are easier. The way that I did it here is more difficult, but it might make us understand more of how to come up with these formulations. Okay, so here we go, 22. It looks like, again, doing x, y, and then z makes the most sense. If we look in the xy, in the xy plane, we've got a triangle that runs from y equals positive 2 to x equals positive 2. So this is the xy plane. And so again, if we're going to integrate with respect to x last, then we set up our rectangle like that. And this curve is going to be y equals negative x plus 2. And then we've got the z thing here, which defines the top part. So the volume we would do is, if we do x last, we'll go from x equals 0 to 2. And then we'll do y next to last, so go from y equals 0, which is the x-axis, to y equals negative x plus 2. And then the final integral will be from z equals 0 to z equals 9 minus x squared dz dy dx. And it would just be, you could switch these two, except if you switched the x and y, you'd have to take this equation and solve for y, which becomes basically the same thing. So you get, if you solve for x, you get x equals negative y plus 2. So if you change that order, you'd have the integral from y equals 0 to y equals 2. So that's from here to here. And in this case, you'd have a horizontal rectangle. And then you'd integrate from x equals 0 to x equals negative y plus 2. And the last one would be the same. You'd integrate from z equals 0 to z equals 9 minus x squared. And it would be dz dx dy. Now again, if you chose to do y and z first, or z and y, you'd have this intersection of this parabolic shape and this plane. This is the equation for plane in 3 dimensions, and it's parallel to the z-axis. So you'd have to find out what the curve of intersection between these two would be as projected into the yz plane, and you could then set that up. So what is that curve? You know, the one we had before, we got a nice linear curve, but that was because there were two parabolas. I think you're going to end with a kind of a parabolic relationship. So these two curves have the same x value. So what you would do is you take these two functions that define those boundaries, and we'd solve for x in the second equation. So you get x is equal to 2 minus y, and then you plug that into here, and you get z is equal to 9 minus 2 minus y squared. So you get z is equal to 9 minus 4 minus 4y plus y squared. And finally, 9 minus 4 is 5. And negative and negative is plus. So you get plus 4y minus y squared. So if we were to plot that, let's just get a graphing program. Let's see what that looks like. And so we got 5 plus 4y minus y squared, except I'm going to use x because that's the variable the program likes. So I got 5 plus 4x minus x squared. And I'm going to go from x equals 0 to x equals what? Well, x in this case is actually y, so y goes from 0 to 2, and y in our case goes from 0, which is to 9, I guess. So there it is. And let's change this to just integers. So this is the curve of intersection. And let me take a picture of that, and then we'll manually change the scale designations so that we okay. So the 0 to 2 part is the y part. So this is actually y, and this one is z. And the curve here, z is equal to 5 plus 4y minus y squared. And what you'd have to do is for part of the interval, well, you'd have two regions again. This would be one region, and you could set it up so that you could define your limits this way, and down here you could do the same thing to figure out what the two integrals would be. And what you would do is we would integrate with respect to y last, and then z, and then x. So let's see if we can figure that one out. So the volume would be the integral from, so we're going to do y last, so you get y equals 0 to 2. You'd go from z equals 0 to z equals 5 plus 4y minus y squared, and the final integral would be in terms of x. So if you go back to this curve, in the region we're looking at is the one that's below this curve. So you get y is equal to negative x plus 2. Or x, we've got to do it x, so x is equal to, goes from 0 to x equals 2 minus y, and it'd be dx dz dy. And then you'd have this second integral, which would be looking at our domain here, so we're looking at this rectangle. So you're still going from y equals 0 to 2. You'd go from z equals 5 plus 4y minus y squared to z is equal to 9. So that's the upper boundary, that's the lower boundary. And then you would have this integral, which would be from x equals 0 to x equals, and what you'd have to do is have to take this equation and solve for x. So if you do that, you'll get x squared equals 9 minus z, or x equals plus or minus the square root of 9 minus z. And this is the plus side, again, because it's on the plus side of the x-axis. So you get plus the square root of 9 minus z. And we'd integrate with respect to x, with respect to z, and with respect to y. So we're keeping the same order of integration. Obviously, doing it the way we did it first makes the most sense from an integration simplification standpoint, but it still should give you the same answer. Okay, and the last thing I'm going to talk about in this triple integrals thing is if we wanted to find the moment of inertia of a sphere around any axis. So we should get the same answer. Now the question is, how do we do that, or is it feasible to do in the x, y, z coordinate system, or would we want to do it in some other coordinate system? Well, I think the answer is we want to do it in some other coordinate system, but at least we could set it up. So we're going to talk about a constant density situation. We're going to have a sphere with a radius of 3. So the sphere of radius 3 in Cartesian coordinates is x squared plus y squared plus z squared equals 9. If we solve for z, then we get z equals the square root of 9 minus x squared minus y squared. And if we let z equal 0 in the xy plane, we get a circle of radius 3. X squared plus y squared equals 9. And you can solve explicitly for y. Y is equal to the square root of 9 minus x squared. And then x would go from 0 to 3. So this is, and the moment of inertia says you take the density and you, so the moment of inertia around the x-axis is you take y squared plus c squared times dz dy dx. So this is the z part, this is the y part, this is the x part. I'm not sure why I have a 4 there instead of just density. So maybe this is assuming a density of 4. I'm not sure why I have a 4 there. And so here is the projection of this sphere. And notice here I'm only integrating, I'm only doing one quadrant here. So really I probably need to integrate from negative 3 to positive 3, from negative the square root of 9 minus x squared to, and then negative the square root of 9 minus x squared minus y squared. And that would get the entire sphere. Now, the point here is that it's very difficult. Okay, so even with these 0 limits, if you take the original function y squared z squared and you integrate with respect to z, you're going to get y squared z plus z cubed over 3, and then you plug in z is equal to the square root of 9 minus x squared minus y squared into here, and if you cube that, you're going to get this to the 3/2 power, or you can factor out the square root. So if you factor out a square root here, you can have the square root times the function, and it quickly goes out of control here. And the question is how would you solve this if you're integrating with respect to y? And you'd have to use trig substitution, and you're like, oh, this is just way too hard. Not that it's impossible, but a lot of times you just have to say, hold on, there's got to be a better solution. Now it turns out there's an example in the book, and the example in the book has a density that's not constant, and as a consequence, it makes the integration much easier than if you have a constant density. You would think non-constant density, but getting an extra factor of y, z, or x into this equation simplifies the whole thing considerably. Okay, I think I've already assigned this, so if not, there it is. So yeah, on Tuesday, let me know if you understood those other ways. I could be wrong. I think I'm right. I hadn't done that before, but I thought it seemed like a good thing to dig into. Okay, moving on. So we're going to go to section 7 now. And you'll notice that it doesn't have any homework. At least it doesn't initially when I first taught the class. I think at this point I was thinking people are probably reaching their mental capacity, and I might be reaching my mental capacity. But so what we're going to do is, in double integrals, we looked at the Cartesian coordinate system, and we looked at the polar coordinate system, and it turns out in a lot of cases the polar coordinate system was much easier to integrate. So when you get to 3 dimensions, there are 2 other coordinate systems that might be advantageous in doing the same problems. Typically they're circular in spherical coordinate systems. Obviously things that are spherical, like spheres, might be a lot easier to deal with. In cylindrical coordinate systems, it's not just cylinders as you think about it, but it could be paraboloids, things that are symmetric around one axis or in the direction. Like you have the axis is the center of the. It's almost like the things we did in chapter 7 where we had a rotationally symmetric object. So for cylindrical coordinate systems, what we have to do is change the limits to the 3 variables. So cylindrical, what you have is you have r and theta, just like you do in polar coordinate systems, and then you have a z coordinate. Now in Cartesian coordinates, the z value is a function of x and y, but in this case z is a function of r and theta instead of us. Otherwise you couldn't really do the integral. And typically the order is you do it with respect to z first, and then you do it with respect to r, and then you do it with respect to theta. So these limits, g1 of theta and g2 of theta, are the radius parts. These are just the angles. And the z function, the limits here are the z limits. Now they're showing here as a function of r cosine theta and r sine theta. That's because r cosine theta is x and r sine theta is y. So a lot of times you're given this function, the z function, well, you're given the limits in terms of z as a function of x and y, and then you convert it to z as a function of r and theta. and then if you have some function you're integrating, so it's not just a volume calculation with an iterated integral, it's actually something integrated, you have to change this function of x, y, z into a function of r, theta, and z. And finally, the dv element is r dz dr d theta. So if you remember, the area element when we did a double integral was r dr d theta. For cylindrical, it's r dz dr d theta. So this takes into account, as you go out in the r theta plane, that your differential elements get bigger as you go out to larger radiuses in that plane. So the actual, once you've got everything converted, it's really not any different than what we've done in terms of procedure, but it's just, a lot of times it's just converting from the function in Cartesian coordinates into cylindrical coordinates. But it's typically when you have the function is z is a function of x squared and y squared, and then x squared plus y squared is equal to r squared. Now this is just talking about kind of the same deal. A lot of times in the if you project into the xy plane, you get a circle, and the circle, if you're defining the limits of integration, they go from negative to square root of the radius squared minus x squared to plus the square root of 9 minus x squared, and then you integrate x from -3 in this case to +3 if you wanted to do it in terms of polar coordinates, which is part of cylindrical coordinates. You'd have the radius go from 0 to 3, and you'd have the angle go from 0 to 2 pi. And this kind of shows you graphically what this differential element looks like. So in just the r theta plane, the xy plane here, it looks just like the differential element for polar coordinates. And then all you do is you then have this dz part to get the volume. So that's why it just adds that dz term. But it's just r dr d theta dz basically. So the first thing we're going to do is we're going to just go through the process of doing the triple integral. So what we have is r z dz dr d theta. Now this r probably was already originally with the differential volume, r dz dr d theta. The function in this case is z, but z, you have to convert that. Well, no, you don't have to convert that, because we're going to integrate with respect to z first. Now, if z were a function more complicated, instead of just z being z, if it was some function of r and theta, z was a function, or this thing was a function of z, r, and theta, then it'd be more difficult. Okay. So here we're integrating from z equals 0 to z equals 2 minus r, which is a, what the heck is that? What is that? Well, what it is 2 minus x squared minus y squared. So you could substitute, and you have to have a square root here as well, because this would be the square root minus 2 minus the square root of x squared plus y squared. So that's z equals that. So I'm not exactly sure what that surface looks like. So this function, the function, if we go back to the original form here, in this case, the function of x, y, and z is just z. The differential element is r dz dr d theta. And I think what we do is just is we just go through the process. So let's do that. So the first integral, we're going to integrate with respect to z. So when we integrate z with respect to z, then you're going to get z squared over 2 evaluated between 0 and 2 minus r. So we plug that in, and then we have d. We've got r, dr, d theta still left over. So we're integrating with respect to z. And then you plug that in, plug the limits in. So you'll get 2 minus r squared divided by 2 minus 2, not 2 minus, just 0. So you get 0 squared over 2. And you multiply by r, dr, d theta. The limits are from 0 to 2 and from 0 to pi over 4. Okay, so all we have to do is multiply this thing out and then integrate with respect to r. So what we'll get is 4. So 2 squared is 4. You'll get minus 4r plus r squared. That whole thing still times r. I'm going to factor out the 2 in the denominator. So that's r. So the r comes out, and then it's going to be multiplied by the term. So we still got one more simplification effort to do here. So I have 4r minus 4r squared plus r cubed times dr d theta. So when we integrate with respect to r, we'll get 4r squared over 2 minus 4r cubed over 3 plus r to the 4th over 4 evaluated between 0 and 2 times d theta. And now we'll plug the numbers in. We're just gonna get a number here. So we're going to have 4 times 2 squared over 2 minus 4 times 2 cubed over 3 plus 2 to the 4th over 4. And you plug in 0 and you get 0. So I'm just going to put that on there times d theta. So we get 1/2 the integral from 0 to pi over 4. So this is 16 halves, which is 8. And here we get 8/32, negative 32 thirds, plus 16 over 4 is 4. D theta, so that's 12. 12 is 36 thirds minus 32 thirds, gives me 4 thirds. Okay, so then we integrate with respect to theta. We could bring the 4 thirds out. You have the integral from 0 to pi over 4 of d theta. The integral of d theta is just theta. So you get 4, well, this cancels out that, so we get 2 thirds theta divided between 0 and pi over 4. And so if you plug pi over 4 in there, you'll get 2 pi over 12 or pi over 6. Is that right? Pi over 4, 2 times pi, 4 times 6, 12, I think. Okay, so that's the answer, I hope. Let me know if it's not. Oh, here it is. Let's see if I got the same answer. Hey, yeah, I got the right answer. Okay. So that was just demonstrating the process you go through. Okay, next one, and we'll just set this up and then we'll work through it in class because it's getting up to 40 minutes here on my timer. So it says convert the following to cylindrical coordinates and integrate. So from a these are the limits, the x limits. Here are the y limits, which is, this is a circle. So that's one good thing. So let's get a piece of graph paper. So I'm going to draw a circle, and it's on a radius of 2. So that's it. And so we go from x equals -2 to x equals +2. This curve is plus the square root of 4 minus x squared. You know, y is equal to that, and here it's y equals negative square root of 4 minus x squared. So in the xy plane here, in terms of r and theta, we have that r is between 0 and 2, or -2 and +2, right? No, just between 0 and 2. So we go from 0 to 2, and then we go from theta 0 to 2 pi. Okay, so that's those two limits. Now the limits here, there's z, so we can leave this one the same. So that's just a horizontal plane at a height of z equals 4. This thing is a, this is z is equal to x squared plus y squared, which is a paraboloid, whatever those things are called. So this is kind of measuring the volume between a flat surface and what's inside this cup-shaped surface. So let's go ahead and just start filling in the blanks here. So we go from theta equals 0 to theta equals 2 pi. We go from r equals 0 to r equals 2. The upper limit is z is equal to 4, and the lower limit is x squared plus y squared, which is r squared. So we can just, we use the substitutions that r squared equals x squared plus y squared. X, we have to put in x is equal to r cosine theta. So that's r cosine theta. And then dz, dy, dx become r dr d theta. Now let's just finish it off. So the first thing, we got to put a dz in there as well. I forgot that. Now let's do r dr d theta dz. So we're going to integrate with respect to z first. So when we integrate with respect to z, we're going to have r squared cosine theta z evaluated between r squared and 4. And then we have dr d theta. So the integral of dz is z. Then we plug those two limits into our z. So we're still, r squared, r and theta are still constants, still considered to be constants. So you'll get 4 minus r squared, dr d theta. And then we'll multiply out these. So we get the cosine of theta, which is going to act like a constant. And then we'll have 4r squared minus r to the 4th, dr d theta. Okay, then we integrate with respect to r, so we can take off the integral here, because we're integrating it now. So we have the cosine of theta, which we treat like a constant, and then you'll have 4r cubed over 3 minus r to the 5th over 5. Evaluated between r equals 0 and r equals 2, and we have our d theta, and we're integrating from 0 to 2 pi. So let's plug that in. So we get the cosine of theta, and inside we get 4 times 2 cubed over 3 minus 2 to the 5th over 5 d theta. So what is that? 8. 8 times 4 is 32, so we get 32 thirds minus 5 cubed is same thing, 32 fifths. So if we convert this to 15ths, we'll get, multiply these together, you get 160. And if you multiply those together, you get 96 all over 15. So that's 64 over 15. I think that's can't simplify that because this is not divisible by 3 or 5. So now we can pull out the 64 fifteenths and go from 0 to 2 pi of d theta, or cosine of theta d theta. And the integral of the cosine of theta is the sine of theta. And we evaluate that between 0 and 2 pi. But the sine of 2 pi and 0 is 0. So I think we get 0. If I did it correctly. Okay, let's see if I've worked through this problem. So here's the plane z equals 4. Here's this paraboloid. And let's go all the way through this thing. And we get 0. Ooh, how about that? Okay, so we're going to stop there. So the question is, how can it be 0? That's the question. Why is it 0? It doesn't make sense. Or does it? Because we have this extra term x. I think that's what's doing it. So if I didn't have x here, I would get a number because it would be the volume contained inside this little eggy shape and this flat line. But because I'm multiplying by x, I've got half the time x is negative and half the time x is positive. And so when I'm basically taking these volumes, and so that they should balance out. So that's probably why it's 0. That kind of makes sense. So if I didn't have x, I shouldn't have gotten 0. But if I didn't have x, then I wouldn't have the cosine of theta. I just have that d theta. Okay, well, see you on Tuesday.